In this section, we will study how to prove an irrational number is actually an irrational number. So, as I said in the very first video of this one, what is an irrational number? An irrational number is something when you convert into decimal, it will not be a terminating decimal, it will not be a recurring decimal, correct? So, such numbers we call it as irrational numbers. So we saw a few examples. So, examples are square root of 2 or square root of any non-perfect square like square root 3. Square root 4 we have 2, so that is not an irrational number. So, square root 5 is an irrational number, square root 6 is an irrational number. So, these are the irrational numbers. Then we have cube root of non-perfect cube like cube root of 3, cube root of 4, cube root of 5. So, these are all irrational numbers. So, our next task is to prove that these are actually irrational numbers. So, now question is how do we prove these are irrational numbers? So, in order to prove these are irrational numbers, what we do is that we end up proving that these irrational numbers cannot be expressed in the form of p by q. So, if it can be expressed in the form of p by q, it becomes rational number, correct? So, that is what we saw. Here we will prove that it cannot be expressed in the form of p by q. So, before going to prove that it is not in the form of p by q, we will study extremely another important theorem. Okay, the theorem states like this. So, let p be a prime number, some prime number, and a be some positive integer. Okay, the theorem states like this. If p divides a square, then p also divides a. Very interesting. So, now this is the new operator that you are studying here. This is just a straight line. Okay, this is read as divides. Alright, divides. P divides a square. So, what does that mean? Is that a square is divisible by p. Okay, similarly, p divides a. This also means that a is divisible by p. Okay, so the theorem states like this. If p divides a square, then definitely p will also divide a. Now, how do we prove this one? So, before going to that, we will revisit our fundamental theorem of arithmetic. So, what does it say? So, if a is any positive integer, we can express a as product of prime numbers. So, that we have already seen. So, a can be expressed as product of some prime numbers. Let us take a can be written as p1 into p2 into so on up to pn. These are all prime factors of a. Now, what are the properties of p1 to pn? One property of p1 to pn is that this is unique. For any given number, this is unique. This will not be any different. What does that mean is that, so if I have got prime numbers p1, p2 up to p1, if these are the prime factors of a, then apart from these things, there will not be any other prime factors that will come here. So, that is what unique means. Alright, so please remember this one. This becomes very powerful argument later. Okay. So, a is now expressed as p1 to pn. So, now what are we saying? P divides a square. So, let us find a square first. So, what will be a square? A square will be p1 into p2 so on up to pn whole square. So, this will be p1 square into p2 square so on up to into pn square. So, now what does it say? So, now it is saying that p divides a square. So, if p divides a square, so what do we understand? If p divides a square. So, a square prime factors we already know. It is p1 square, p2 square, pn square. And now we are saying that p also divides a square, which means p is one of the prime factors of a square. And we also know that by uniqueness, just now as we saw the property, that apart from p1 to pn, there are no other prime factors. But now I am saying p is another prime factor. So, when is this possible? So, it is possible only when p is one of these. I hope you understood this one. So, a square's prime factors are p1 square, p2 square up to pn square. So, apart from p1 up to pn, there are no other prime factors. But when I say if p divides a square, now I am claiming that p is another prime number which divides a square. But just now I said that a square prime factors are only p1 to pn. And now I am saying p is another prime factor. So, when is this possible? It is possible only if p is one of these. I hope you understood this one. So, if p divides a square, then p must be one of P1 up to Pn. So it must be one of these. Otherwise, there is no way that P could be. Otherwise, there is no way that P could divide A square. All right. So if P is one of these, so what does that mean? Now the prime. For our convenience, let Pn be P. Let's assume that Pn is P. Okay. So if Pn is P, then what happens to A now? So now, therefore, A can now be written as P1 into P2, so on up to Pn. Pn we now assumed it as P. So now you see the prime factors of A are P1 up to P1, P2, and finally ending with P. So P is now one of the prime factors of A. So therefore, P also divides A. I hope you understood. So what is the argument here? P divides A square. So I am claiming that P is one of the prime factors of A square. But here we said that prime factors are P1, P2 up to Pn. So this is possible only if P is one of these. So for our convenience, we assume let Pn be P. So if Pn is P, then we rewrite this equation. So A can now be written as P1, P2 up to P. So now what happened here? P is one of the factors, prime factors of A. So if P is one of the prime factors of A, then P also divides A. Please understand this carefully. Very powerful theorem. We are going to use this one multiple times. One analysis that can be done here is that if P divides A square, P also divides A. You can generalize this one. If P divides A cube, then P also divides A. Obvious. If P divides A raised to 4, then P again divides A. If P divides A raised to n in general, then P will again divide A. So if P divides any power of A, then P definitely will divide A. That is one simple analysis that you can make out of this one. So now we are going to use this theorem in order to prove irrationality of numbers. We will see how to do that in the very next lecture.